Hi, ladies and gentlemen. We had previously started talking about quantum theory, about how light has a dual nature, both as a particle and as a wave. But it's a particle in nature that got proven to exist due to the photoelectric effect. We had previously spoken about how a photocell can absorb a photon and then emit an electron, just like it happens in this demo over here, where a photon, the energy of the photon, pause that for a moment over here, the energy of the photon itself, E, which we can solve for the amount by using Planck's formula of HF. That photon strikes the electron. And when it strikes the electron, it gets absorbed. This energy gets used up. And it gets used up to do two things. First of all, it frees the electron from the atom. And at the same time, it gave the electron a certain amount of kinetic energy as it's traveling along. Okay? And eventually, of course, that electron can get recaptured by the atom itself, and when it gets recaptured, it will then release the photon afterwards. But taking into the idea that ultimately the maximum kinetic energy of the electron is ultimately equal to the energy of the photon itself minus however much energy was used to free the electron in the first place. And we call that the work function. I know it has the same symbol as flux from the previous unit, but there's no little m here, so it's completely different. So flux over here, so the work function here is represented by the same variable. This HF is just a reminder that, of course, that energy of a photon is equal to HF. So this is still energy of the photon. And whenever we're dealing with energy, we can deal with it either in joules again or electron volts, depending on whether we're using Planck's constant as 6.63 times 10 to the negative 34 joule seconds, or if we're using 4.14 times 10 to the negative 15 electron volt seconds. But understand, so ultimately, the energy that the electron has afterwards is based on how much energy the photon gave it minus the energy used up by the surface to release that electron, okay? And we can deal with this more in the next simulation, but keep in mind what exactly is work function and how we can solve for this, because we're going to answer this question right now in the simulation. Okay. So yesterday we spoke about how when you shoot photons onto a surface, if the frequency is too low, there's not enough energy. And that energy isn't enough to overcome the work function of the surface to knock an electron out. But as I decrease the wavelength and increase the frequency, eventually I reach a point where electrons are going to start to come out. Okay? In this case, it happened around 500 nanometers. And the higher I increase the frequency and decrease the wavelength, you can see the more energy those electrons have, individual electrons have. In other words, they're moving faster than before. Okay? Keep in mind over here this graph. In fact, let's take a look at this graph again, right over here, as compared to before. In this graph, they noted that there was a certain minimum frequency needed to knock an electron out. We had previously called that the threshold frequency. So since we know the minimum frequency needed to knock an electron out, then in order to solve for the minimum energy needed by the photon, we'll just solve for energy all over again. H times the threshold frequency. Because by solving it times the threshold frequency, we can solve for the minimum energy. And that minimum energy is, of course, the same thing as the work function. Okay? So the work function is just equal to hf naught. It's the same formula as the energy formula from before, but the only difference is that it understands that we're dealing with a minimum frequency. So if I wanted to solve for this in electron volts, okay, I would use 4.14 times 10 to the negative 15 electron volt seconds, and the frequency is approximately 0.55 or 5.5 times 10 to the 14. I would end up with a work function of approximately 2.3 electron volts, meaning that this is the minimum amount of energy needed to knock an electron out. Okay, so if a photon had more than 2.3 electron volts, then the extra energy would turn to the kinetic energy of the electron. Okay, and let's actually take a look at our simulation just to make sure that that is happening. So right now we have a graph here. Let's move it to approximately 200 nanometers. Okay, so right now we're shining ultraviolet light onto the sodium surface. If I wanted to figure out how much energy that ultraviolet light had, I could use my original formula of E equals HF, or in this case, because they gave me the wavelength in nanometers, it's much easier to use HC over lambda, because I have a value of HC given to me in electron volts and nanometers. So HC is a constant in the reference table of 1240 eV/nm divided by approximately 200 nanometers. I find that the energy of the individual photon to be 6.2 electron volts. This is the energy of the photon. So all these little sparkles that are shining out, each one has 6.2 electron volts. But this surface we had just calculated needs at least 2.3 electron volts to knock an electron out. So after the 6.2 hits the surface, 2.3 gets used up, and then the rest becomes kinetic energy. So in other words, the kinetic energy of these individual electrons shooting through is equal to the energy of the photon minus the work function of the surface. So we equal to 6.2 electron volts minus 2.3 electron volts, which is approximately 3.9 electron volts. And notice on our graph over here that it tells us this is the energy of the electron. Okay, so the energy of the electron is approximately 4 electron volts right now, when the light shining onto it is ultraviolet of 1.5 times 10 to the 15th. So it matches the graph. Okay. So just to recap, work function is ultimately just means the minimum frequency needed to knock an electron out, or you can think of it as the maximum wavelength, of course, as well, if we were talking about threshold wavelength instead of threshold frequency. So let's just do a quick practice problem in 15. What is the maximum kinetic energy and speed of an electron ejected from sodium surface whose work function is 2.28 electron volts, which is actually approximately what we had calculated, so it worked out perfectly. When illuminated by light of 410 nanometers and 550 nanometers. So understand, okay, if I just were to diagram this, that there's some sort of surface with a work function of 2.28 electron volts. We have 410 nanometer light and 550. So 410 is a low wavelength, high frequency. And we have another light shining on it, maybe it's green perhaps, of 550 nanometer light shining on it. And they want to know what's the kinetic energy and speed of those electrons knocked out. Well, the first thing you should always do is convert everything into energy. So if I know the wavelength of light, so with the blue, the energy is equal to hc over lambda, so equals to 1240 electron volt nanometers divided by 410 nanometers, which equals to 3.02 electron volts. With the green light, I would have the 1240 electron volt nanometers divided by the 550 nanometers, which gives me 2.25 electron volts. Now notice, is that 2.25 enough to actually knock an electron out? No. So in other words, this wouldn't even be able to create an electron at all. It's not past the threshold frequency, or really the work function. So in this case, only the 3.02 will create an electron, and we can calculate the kinetic energy of the electron simply by subtracting the energy of the photon and the work function of the surface. So with 3.02 minus 2.28, we end up with 0.74 electron volts. Okay? But what about the speed? Well, let's bring this over onto the whiteboard over here. Okay. Only because we're going to need a lot of space for this. If I wanted to calculate speed, now I do know the kinetic energy of the electron already is 0.74 electron volts. And of course, we all know that the kinetic energy formula is 1/2 mv squared. However, you have to remember that kinetic energy is an old mechanics term. And in mechanics, we never use electron volts, we always use joules. So first step would be to convert this into joules. Knowing that 0.74 electron volts, do a quick conversion factor. 1 electron volt is 1.6 times 10 to the negative 19 joules. I get the energy equal to 1.184 times 10 to the negative 19 joules, which then I can say equal to 1/2 mv squared. Okay, we know the mass, of course, of an electron to be 9.11 times 10 to the negative 31 kilograms. So then the velocity is equal to kinetic energy over mass, which will equal to 5.1 times 10 to the 5th meters per second. Okay, so now we can solve for the speed of the electron as well that's coming off. Okay. Now the next part is a little bit interesting about the stopping potential or stopping voltage. And it's easier to demonstrate with a simulation than to actually simply explain. We can see that the circuit is connected to a battery source over here, And we have an ammeter over here that measures how much current is going through with all those electrons coming in. Now, if we were to actually flip that battery around and increase the strength of the charges, meaning that we're increasing the strength of the plates themselves, you can see that once I reach a certain point, the current became zero. In other words, that battery stopped all electrons from coming through. Even though there was a photoelectric push for the electrons to go one way, the battery itself is pushing with its own electrons the other way, and the two collide and eventually cancel out. But look at the number, 4 volts. This is the stopping potential. VO, stopping potential, is 4 volts. Look at how much energy those electrons had. 4 electron volts. Well, remember, when we normally solve for the energy to move an electron, it's Q times V. In other words, we have 1 electron moving through a certain number of volts, then it ends up being the same amount of energy. So whenever I attach a battery to it, I can solve for how much kinetic energy those electrons actually have by simply measuring the stopping potential. So the stopping potential prevents photoelectric current from passing through. And the stopping potential will always be directly related to kinetic energy of the electrons themselves. Okay, the maximum kinetic energy. So what we saw was when the stopping potential was 4 volts, the kinetic energy of the electron was 4 electron volts.